Thank you everyone for joining. This is our fourth webinar on aerial thermal imaging. Tim Mammatt, our CTO, will be providing the insights today into aerial thermal imaging, covering drone applications, payloads, and data processing. Before we start, I just want to explain that we have several pauses throughout the webinar and at the end, so you can ask any questions you may have in those intervals. Please do this either by raising your hand, which should be at the top of your screen, and unmuting your mic to speak, or write in the Q&A box, which is also along the top of your screen, and Tim will answer any questions from there. Throughout the webinar, please keep your mics muted if that's okay as well. If you have any issues throughout the webinar, please write this in the chat box, which I'll be monitoring, and I'll try and help sort any problems. So yeah, I think that's all the housekeeping done, so I'll pass over to Tim to begin the webinar.
Right, good morning, afternoon and evening. I think we were due to have people from all over the planet on this. Yeah, welcome all, thanks for joining. I'll be giving a talk today on sort of an introduction to thermal imaging. Just a very quick sort of disclaimer, as I'll go through in a moment. Just this is deemed essentially very high level, like an overview of thermal imaging. There is far more to it, and it shouldn't be considered, sort of formal training. And that, if you do want to know more, we'll sort of discuss the next steps with you towards the end. But moving on, just a little bit about the company. So Ether is a brand that we founded in 2020 under Vantage UAV. We've now got 30 plus employees across the US and Malta and the UK. We are what's deemed a drone solutions provider. So we work with a lot of companies who are wanting to implement drone services into their existing offering to either provide their clients or to use internally. And we help them essentially with every step in that process. We are partnered with a lot of the major drone and sensor manufacturers, including DJI, Ace-Core, Quantum Systems, and so on. And we pretty much cover the majority of verticals going. We've got expertise in the majority of them. And as of next month, we will open up our second office in the US, where we'll be providing something very similar, but all under the Vantage UAV brand. Okay, so a little bit about myself. I'm Tim Mammatt. I'm the group CTO of Vantage UAV and Ether. Back in 2020, when I joined the company, my route was to essentially establish the drone solutions brand Ether. I've been in the thermal imaging in the drone sector since 2012, when the thermal imaging cameras weighed multiple kilos and the drone was over a meter wide, and it flew for 5 minutes. We thought that was fantastic. 9 of those years was working for a specialist thermographic consultancy where we utilised thermal imaging across pretty much every sector going, predominantly the built environment and electromechanical testing, but also for public safety, agriculture, utilities inspections. And we're working with a doctor up in London on breast cancer detection. And we've also worked with quite a few universities on thermal imaging projects and research initiatives there. I'm also the creator of Thermo Converter, which is a bit of software we developed, but I'll cover that more later on. So just a quick summary of what we're going to be covering today. I'm going to give a very high level introduction to thermography, because there is a vast amount of science behind it. And I want to try and keep things simple for everyone in this instance. We're going to talk about how then we're using thermal imaging from the air on drones predominantly, but of course it can be on helicopters and fixed wing aircraft. I'm going to sort of cover some of the applications, the pros and cons of using thermal imaging from a drone. I'll then go through thermal imaging payloads, the specs for them, which you would typically see on the manufacturer's websites, what they mean, and what would be the best suited sort of features for your particular application. Of course, I can't say any of this without mentioning the thermography training, which we'll sort of cover in a bit more detail towards the end, as if you are looking to use thermal imaging, this is essential. And then, of course, we'll go through some workflows for thermal imaging, and then we'll finish off with a final Q&A if anyone has any subsequent questions. As mentioned by Emily, if any questions come to mind whilst I'm going through this, then please use the Q&A section or raise your hand, and I'll be able to address those as and when. Okay, as mentioned before, it shouldn't be a substitute for thermography training. It is very high level, and that anyone who wants to use this in a professional capacity, then I'd recommend you follow the next steps that I'll discuss towards the end of this. Okay, so firstly, what is thermal imaging? So essentially, every object, everything that has a temperature above absolute zero or 0 Kelvin emits infrared radiation. And by using specialist sensors and filters, we can detect this. And we do this by essentially gathering the thermal radiation and focusing it via a lens, which is normally germanium. And this focuses it on a sensor, which in most cases is called a microbolometer and is uncooled. This in turn turns that radiation into electrical signals that then can be converted into temperature values through calibration. And then once we have those values, we can assign false color to it to produce a thermogram or a thermal image. And then depending on the type of data that's captured, you can then manipulate that data to focus on different temperatures. You can change the colors and so on and so forth. I won't go into too much detail, but there are quite a few influencing factors that can affect the temperature value of something, such as the reflected apparent temperature, the emissivity, which is how much radiation it absorbs or transmits or reflects. Sorry, let someone else wants to jump in. Okay. And I know we were due to have some Americans on this, so I will be using Celsius, but typically the values are in Celsius or Fahrenheit. The lens material is worth noting is normally a substance called germanium, which is transparent to infrared radiation. This normally has an additional coating on the end, which you'll see on any thermal imaging camera, which is there to reflect more of the visible light. So, aerial thermal imaging. Essentially, it's a thermal imaging camera mounted on an aircraft, be it a drone, helicopter, or a fixed wing. And sort of many years ago, you used to see them, sort of this sort of size here, where they were really big, really heavy. They had massive lenses on them to be able to focus the infrared radiation so that they could get detail at a greater distance. And now, sort of just I think it's about 18 months or so ago, we're now sort of seeing sensors this sort of size with very good performance and specifications. And I think there's been a number of influencing factors for this, be it the adoption of the technology and how useful it has been across multiple industries. We've also seen DJI partner with the market leaders in thermal imaging, which was FLIR, which is now Teledyne FLIR, and they had a collaboration to produce essentially a mass market payload for initially the Matrice 200 series, and now they've partnered with a company called Infrared to produce much smaller cores, which are manufactured and produced in China, so they've reduced the costs of these systems somewhat further. So yeah, we've seen a massive reduction in size, weight, and power, and this has caused a massive influx of drones now with thermal imaging capabilities. The majority of them have been simplified to the point where it's essentially plug and play. We've all seen the DJI payloads, which you just screw in, turn on the aircraft, and away you go. But of course, it does go without saying that you still need to have a good level of knowledge in how to interpret this data and how to manipulate it depending on your particular application. So we've got some common applications of thermal imaging here. One of the more sort of popular ones that we see on police camera action, is public safety, where they're, hunting down suspects, using a helicopter. You often see that black-white temperature palettes that they use to try and follow or locate the suspect. Search and rescue is obviously a great application for it. It enables you to cover vast areas of land and just focusing on any thermal anomalies that you might come across. It's now starting to be used in the wind sector. We've developed a technique for looking at wind turbine blades, and with the thermal imaging, you can see essentially any subsurface defects up to about 15 centimeters or so, and this can be delamination or faults within the blade itself. And any sort of air gaps, or in fact, one instance we were able to find where someone had shot one of the blades, and the bullet hole. Oh, sorry guys, let's get rid of that. We caused water to enter the blade, and we were able to see the exact path of that water, so that it could be repaired. The built environment is definitely one of the larger applications for us as well, particularly in the colder regions, because it enables you to see things like heat loss through discontinuity of insulation, where there might be wet or damaged or missing insulation, where there's thermal bridging, which is where the material is essentially drawing that heat to the external elevations and cooling the building down. And then internally, you can also then use it for things like thermal comfort. So if it's like a housing association or a mass residency, then you can see how the temperatures are internally and whether or not the occupants are likely to feel any discomfort from any cold drafts. Solar is another popular application. Essentially, a lot of the faults, when they occur, they fail and produce a heat temperature signature, and that can be detected with a thermal imaging camera. And that can be things like substring faults, damaged cells, faulty diodes, and so on. Oil and gas is another one. Typically, we see optical gas imaging cameras, which I'll mention later on, which are a mid-wave camera, which enables them to detect gases. So it's very useful for leak detection. However, there's quite a few nuances around using it, and the distance of the drone or the camera from the leak comes into play quite a bit. Agriculture is another one, and is typically used for things like livestock monitoring. A lot of our American clients have massive ranches, and they need to be able to find missing livestock, or if they have any trespassers on their property. And of course, you can, because water absorbs solar radiation, it has a much higher specific heat capacity. It holds onto that temperature for longer, and it takes longer for it to warm up. So you can actually see the moisture content in the soil and on the land, where there's any pooling, quite clearly using a thermal imaging camera. Of course, these are just a few examples. It's almost at least every day we're hearing of another use for it. Okay. So yeah, essentially the applications are endless. Anything with a temperature difference, you can use thermal imaging camera to exploit that. So here's a very quick sort of image that we took out in the field the other day with quite some foggy weather in Chichester. So I got one of our pilots to quickly nip out with our Mammatt 2 Enterprise Advanced to sort of capture some example images. I know it's quite small on the screen, but you can see clearly here with the visual camera, the visibility is very poor. However, when you switch to thermal, you can clearly see there is a temperature anomaly. In this case, it's the pilot in the field. So that enables for rapid location of missing persons, dogs, and other animals. We're now starting to also see a lot of companies utilizing things like artificial intelligence for automatically identifying anomalies. We're seeing it particularly in the solar side of things, where you've got very very similar panels, and so it's quite easy to detect edges and then pick up the temperature values and then create reports detailing the exact location of the hotspots, which can then be investigated further. So key advantages of using thermal imaging. I mean, lately, obviously, the size is reduced. They're very portable now and lightweight. So we're seeing more and more drones that are capable of lifting them. And using a drone with thermal imaging camera, you can cover quite a large area of land, and it also provides you with a different perspective. So if you're looking at, say, a field, then it enables you to get that bird's eye view to locate any potential issues. You can read hard to access locations. If you're doing rooftop heat loss surveys, that sort of thing, you can use them for that. And as seen in that foggy image earlier, it does provide far better visibility in low light or poor visibility scenarios. And of course, because everything is transmitting infrared radiation, you can use them at night time. They are now relatively affordable. We have seen the price decrease somewhat significantly in the past sort of decade, where previously you'd be looking at sort of £25,000 or more, but now you can get a complete thermal imaging package on a drone for less than 5,000. Most of the cameras have reasonably good accuracy. You've got plus or minus 2 degrees. It seems to vary depending on the camera. Plus or minus 5 is another commonly referenced spec. This is, of course, if it is radiometric. I will cover what radiometry is later on. But in non-radiometric cameras, you can see anywhere between 10 to 20 degree Celsius variation. And sensitivity of the cameras has increased. This is often referred to NETD, noise equivalent temperature difference. So we're looking at most cameras now under 100 millikelvin. Most seem to be around the 50 millikelvin, which provides a much smaller temperature difference that you'll be able to see, and it will give you a more detailed thermal image. And of course, with radiometric cameras, you are storing that temperature data within the image itself, so you can analyze that when you're doing the post-processing and building your reports. So whilst I mentioned the cost being an advantage, it also is a disadvantage because it is still more expensive than your typical drone with an RGB camera. This is normally sort of 2 to 3 times the price. And whilst the accuracy has improved over the recent years, it's not necessarily as good as the ground-based cameras, where you can get as good as sort of plus or minus 1 degree difference. Of course, you're limited by the flight time on a drone. Most are between 20 and 40 minutes. You can get much larger aircraft now, which can exceed the hour mark, but you are somewhat limited, particularly bearing in mind that a handheld camera is typically 2 to 4 hours of battery life. While sensitive is good, it might not be best for research applications. If you're really looking at very small temperature differences, you might then require something like a shortwave or a cooled camera where you can get 10 to 20 millikelvin things. And of course, you can use these drones. You can only use outside, although I have heard of people who have created handheld mounts for them so that they can use them inside. But more often than not, the focus is fixed at infinity, so you have to play around somewhat to be able to get it to work internally. Distance is a disadvantage for thermal, particularly if you're looking to get accurate temperature values. I will go into more detail in a slide later on. Of course, you can't see through water, so when it's raining, if any water gets on the lens, then it's going to distort and essentially block out the image. As mentioned with the distance, you can't necessarily identify early on what an object is that you're looking at. So if you can see a heat source, you might not necessarily know what it is. You might just see a hot spot on your screen, and it requires you to get closer to that object to then be able to get that detail required to identify it, which is quite important, certainly in the military and the security side of things. Of course, with thermal imaging cameras, we're looking at the temperature differences between objects in the built environment. You typically want a 10-degree difference between inside and out. So if you're outside on a hot sunny day, with an ambient air temperature of 30 degrees, it's very close temperature to, say, a person's skin temperature. So you're going to have quite a lot of difficulty being able to isolate that sort of temperature value to be able to locate that person. Yeah, you certainly see that in the UK on hot sunny days, or certainly in the States or in any desert areas. It becomes very difficult to actually locate those hotspots. Of course, if it's at night, so you've got a much lower temperature, then it's generally easier to locate those. So as mentioned with the distance, if you're looking to accurately measure the temperature of something, then you need to have at least 3 pixels on the detector to cover that particular object. So if you're quite far away, turn on laser pointer, you've only got, in this instance, you've got 1 pixel covering it. So, and not all of that pixel is covering it either. So you're going to have a very hard time actually getting a usable temperature value, because you're also now taking into account the surroundings. So if you get much closer to the objects, then you've got far greater coverage. And then typically in the software or on the screen, you have spots as opposed to pixels. So that will normally average 3 by 3 to give you that more accurate temperature value. So this is in cameras, is often referred to as an instantaneous field of view when you're looking at the specs, and that will give you a degree field of view per pixel on that camera. It's often referred to as well as sort of the spot size ratio. So in this example, if the object is 36 meters away, then the spot size is 1 meter. Although in reality, with the higher resolution cameras nowadays, then that's far lower. There are some particular applications that have standards that do require you to have essentially a certain spot size. There's one in the solar industry where it's called IEC 624463, which requires you to have a spot size of 3 centimeters. So you need to get essentially 5 of those pixels on each panel, in each cell, to be able to get an accurate temperature value. Just to give you an example of sort of the distance you need to be away from the solar panel, in that instance, if you're using a 640 by 512 pixel camera with a 45-degree field of view, then you need to be flying above the panel about 20 meters or so away, which isn't necessarily ideal when you've got things like power lines and pylons and trees around the area. So thermal payloads. So I'm going to quickly cover some of the sort of the key specifications of them. There are generally 2 main types of thermal imaging cameras: uncooled and cooled. The cooled cameras, because they have an additional cooling components, are generally much larger. They also obviously heavier because of that. Yeah, so they sort of generally operate in different wavelengths as well. They also use things like liquid helium for cooling, which requires recharging. So you have a much shorter maintenance window to sort of keep that camera cooled and performing as it should. Most common is long wave infrared cameras. You'll pretty much 90% of the cameras on the market at least will be uncooled microbolometers in the long wavelength spectral band. We also have mid-wave, which is generally used for gas detection. And these are normally cooled cameras, and you can see this particular one here, which is an optical gas imaging camera. It's much larger than your traditional long wavelength infrared camera. And then you do get short wavelengths, which covers a different part of the spectral band, the infrared spectral band that is, which is normally between 3 and 5 microns, which can be used for looking through certain material, but they are much larger, more expensive. We're talking at least 6 figures in some instances, and they're generally used for very specialist applications. Most nowadays are plug and play. They often come integrated onto a gimbal, particularly in the DJI side of things. And these are literally just, you plug it into the camera, you turn the drone on, and away you go. There are, of course, a lot of standalone sensors, which, like the boson cores from Teledyne FLIR, which do require additional integration time and components to be able to get them performing as they should. So resolution, that's often one of the more popular and sought after specification of the camera. Back when we first started seeing the smaller payloads enter the drone industry, they were around the 160 by 120 pixel resolution. So compared to your typical RGB camera, which are 20, 30 plus megapixels, thermal imaging cameras are far less, because essentially you have to think of every one of those pixels as almost like a tiny thermometer, which is why they're very expensive. 320 by 240 is 4 times that, and then 640 by 480 or 640 by 512 is another common resolution. It's definitely the most popular, and we're now starting to see more cameras enter the drone market, which have sort of exceeded that. So we're looking at sort of 64 times the original resolution of the far smaller sensors, and these are now starting to enter the market at sort of more affordable prices. You may have heard of super resolution. This is where you're essentially using the movement of the camera to stack 4 images together to essentially quadruple the resolution. So you'll see, particularly on the new DJI M30T, it's a 640 by 512 camera, but it actually has super resolution, which will combine it into a 1280 by 1024 pixel resolution. And it's still radiometric, it's still temperature data, so you are then going to get a more detailed image. The field of view, now this is very sort of application specific. Obviously, with a narrower field of view, you increase the detail at a distance. So this is good for sort of search and rescue in some instances where you're wanting to actually identify a hotspot. The military, you'll certainly see things like the thermal optics on a lot of the weaponry will have a very narrow field of view. But however, if you're wanting to cover a far larger area, again, throwing back to search and rescue, you need to be able to find a hotspot to investigate. Then you're going to want to have a wider field of view, and we typically see sort of 45 to 50 degrees for those. One of the issues is when you increase the FOV, the opticals do start causing almost like this fisheye effect, which you can see down here in the lower right image. And this can distort the image somewhat. So if you're trying to look for an accurate reference on a visual image, then you're going to have a hard time comparing those. Generally speaking, the narrower the FOV, the larger the optic on it. In which case, in most cases, it's a germanium lens. So this drastically increases in size with a narrower FOV, and this increases the weight and, of course, the cost. So you might have heard of radiometric and non-radiometric cameras. Now, radiometric or radiometry is where the temperature data is stored in the image. And this and that allows for you to then perform post-analysis on the image, where you can then manipulate that data to suit your intended application. You normally do this through the manufacturer supplied software. However, it does go without saying, if you are using a non-radiometric camera, then more often than not, they will give you a temperature value on the screen in real time. But when you save that image, you won't retain that temperature data. So in inspection and surveying applications, you more likely than not need to keep that data. However, if you're doing search and rescue or you're just looking for hotspots, then you don't necessarily need to have a radiometric camera. Non-radiometric cameras often have a setting where they'll take the lowest temperature on the particular scene and the highest temperature, and it will adjust the color palette and the scale according to that. So you'll often see when you go from looking at a cold object to a hot object, all of a sudden the color gradients will change, and that's now because it's introduced a much higher temperature value and it's adjusted to that. Radiometric cameras often have far better accuracy. As mentioned before, we often see sort of 10 to 20 degree variation with the non-radiometric cameras. So in most instances, we would always recommend the radiometric cameras over the non-radiometric. Although I think nowadays most cameras are radiometric. So I'm not quite sure how well this is going to stream. So most cameras have a certain frame rate. 9 hertz is the most common. Now, this is quite low because it's not controlled by the US government. They have very tight restrictions on thermal imaging sensors that could be used for, say, heat-seeking missiles or guidance systems. So they have very strict export restrictions on these. There are then regional restrictions. So in the UK, if we were to produce a British thermal imaging sensor, we wouldn't necessarily be able to export that to certain countries without having a license in place. So if you are buying from abroad or you're looking to sell abroad, then always check your sort of your local restrictions and any much larger export restrictions that might apply to it. Because there have been people go to prison, certainly over in the States, for trying to supply this sort of equipment to more unfriendly countries. I'm going to see if this video plays. I don't know how well it's going to come across on your screen, but my colleague will send over a link anyway in case you want to watch it later. This comparison was produced by RMUS over in the States. I thought it was quite appropriate for this. Let me just. So hopefully that is displaying essentially the right image here. Let me see if I can turn off the audio. No, it's not going to let me. Yeah, there we go. So this right image here is 30 hertz, and you can see hopefully you can see the image is far smoother. Whereas, okay, no, Emily's shaking her head saying it isn't. So I'll leave it at that. But the 9 hertz camera is presenting that data 9 times a second. So if you have a moving object, then it's going to appear very choppy on your screen. So generally speaking, if the drone's going to be moving or the particular object you're looking at is going to be moving, then you'll want to go with a faster frame rate. And nowadays, we're seeing cameras that are 25 to 30 hertz, sometimes greater than that. But yeah, you do have to bear in mind any sort of export restrictions on that. 9 hertz is often cheaper. It's a lower spec. And it's not entirely useless. You can use it when you're looking at, say, buildings, which are static objects, and you won't sort of suffer from any loss in performance. Yeah, okay. So some example payloads and payload manufacturers. We've probably all heard of DJI. They've got quite a few cameras now in their product portfolio. The H20T, H20N for the Matrice 300 series. And then we have the Mammatt 2 Enterprise Advanced, which is a drone itself with a 640 by 512 payload, which comes under the sort of the £5 price point as well, with making it a very attractive thermal imaging drone for inspection, public safety, and so on and so forth. And then they've just announced and released the M30T, which has a 640 by 512 resolution camera with super resolution, taking it up to that far higher resolution. Teledyne FLIR, as they're now known as, they generally produce the cords. It's only sort of the past sort of 4 or 5 years they've actually started producing their own drone-specific payloads. We've got the TZ20 and the TZ20R, which is the radiometric version, and I will cover that one later on because it has quite an interesting feature. You then have the Hadron unit, which is a visual and a thermal core combined, which is designed for OEMs looking to integrate thermal imaging capabilities into their drone platform. And then we have the boson cores, which are very, very small thermal sensors that are now being integrated into many other sort of payloads by dozens of other manufacturers. Workswell is probably a less well-known company based over in Czech Republic, and they produce their own payloads standalone, so they do require some integration, and they call them the Wireless Pro S1. You've got Wireless Security, which has I think it's 800 by 400 non-radiometric resolution, and they also provide and produce a gas imaging system for optical gas imager, which is at the 320 by 240 pixel resolution. And there are dozens of brands. There's a lot more in the handheld side of things. Fluke may have heard of, Sierra Olympics. There's many of them, but these are definitely the more popular ones. So it was, as mentioned, got the H20T from DJI. This is a radiometric camera. It has a combined RGB cameras. It's got a wide angle and a zoom camera, and it has a laser rangefinder. It's 30 hertz, so you're getting a relatively smooth image. It does only have digital zoom, so essentially you're decreasing the amount of pixels to enlarge the image, so you're not necessarily getting any more detail at a distance. It operates in the long wavelength part of the infrared spectral band. It's got a relatively good sensitivity of 50 millikelvin or under, and it's relatively affordable compared to some of the handheld cameras of the similar specs. This makes it ideal for public safety and inspections, but it has been known to be used for many other sort of applications as well. Now, I wanted to specifically mention the TZ20R by Teledyne FLIR. This is their radiometric version, and they advertise this as having thermal zoom, optical zoom, which it does and it doesn't. It does because it does have the ability to zoom in essentially 5 times optically on a target, but it does this by using 2 different thermal imaging cores with different field of view. You've got the wide field of view at 95 degrees, and then the narrow one, which is this small, which is the larger optical lens you can see on the right hand side, and it literally just swaps the image over from one to the other to give you that zoom capabilities without the loss of detail. So this is a fantastic camera, certainly in the search and rescue side of things, because it enables you to use the wide angle field of view to cover far larger areas. And then if you find a heat source or a hotspot, you can then switch to the zoom lens, and you're getting far more detail to be able to tell you whether it's a person or just a wild animal or something like that. So on to training. As mentioned, if you're looking to sort of seek a career or add thermal imaging into your service offerings, I strongly recommend that you go out and get training. One of our training partners, iRed, who I notice are also on this call. So hi, Steve. I'll see you down there. So iRed are a specialist thermal imaging training and inspection company, and they provide a wide range of courses. So we've partnered with them because we have many clients who are looking to get on board the thermal imaging side of things. So we recommend that before you purchase a camera or you start providing the service, if you already have one, that you get some formal qualifications under your belt, so you can then have that confidence in your data, which you're then handing over to your client. And in some particular cases, actually having a formal qualification is a necessity. Insurance companies now are starting to specify that you need to have a level 1 qualification. And for some certain schemes, such as BREEAM, which is in the built environment, if you're looking to get a BREEAM credit, you need to have a thermographic survey carried out of your building, and that needs to be signed off by a level 2 thermographer. It's not just point and shoot. I know manufacturers have simplified using these cameras to the point where they are plug and play, but there are many factors that can affect things like temperature readings, reflected apparent temperature, the emissivity of an object. So all of that needs to be considered when you actually go out and start collecting this data and using these thermal imaging cameras. Of course, this does differ from region to region. In the UK, we have different schemes to over in the US, but generally speaking, it's level 1 and level 2. Level 1 would normally see is the sort of the data collection side of things. So if you're just collecting data, which will be then handed off to a level 2 thermographer, who will then perform the analysis on that and produce the report. There is a difference between certification and accreditation. You'll see that Thermo and Fleur have their own thermography certifications. Now that is something that is essentially certified by them, whereas something with an accreditation is where it's the training provider and the training material is audited by a third party. And in the UK, we have the PCN, Personal Certificate and NDT accreditation scheme, which adds that accreditation under your belt. And IRED are a provider of this. And we have, for the sake of this webinar, managed to get a 10% discount on anyone looking to go on the course there with the code ETHA10. So, typical workflow when using thermal imaging. This does differ from application to application. So in this instance, I've tried to keep it pretty general, but I'm using a solar park as the subject matter in this instance. And this would typically apply just to the sort of the inspection and the surveying side of things. You wouldn't necessarily be using anything like this when it comes to, say, search and rescue, because that's very ad hoc, and often or not you're called out in an emergency, and there's very little planning. So planning, of course, you need to have the good weather conditions, not just for flying in, but for actually collecting accurate thermal data. If it's been raining, then you can forget about it. That water and that moisture content is going to skew any thermal results that you're after. Of course, you need to have the right equipment. As mentioned before, in the solar side of things, if you're wanting to capture the data performing to that standard, then you need to make sure you've got appropriate field of view and resolution to be able to collect that data safely without risk of hitting a power line or something like that. So yeah, you need to make sure you're appropriate distance, which can obviously affect the safety, particularly when operating with a drone. And then, of course, your usual flight planning. So when it comes to carrying out the survey, there are numerous things that need to be done before you start flying. The thermal imaging camera will need to acclimatize to its ambient air temperature. You can't just leave it outside with power off and everything. The camera needs to be switched on and sat there, acclimatizing to the ambient temperatures, and that will avoid what's called a non-uniform calibration, which is a small shutter inside most cameras, which essentially calibrates the camera so it's got a uniform temperature across it, and that will then produce the most accurate temperature values. If you don't let your camera acclimatize, you'll often be flying midway through the flight, you'll hear that shutter or you'll see the indicator on the screen, and that will then affect the color gradients of your image and the temperature values. So you need to let that camera sit there turned on for normally around sort of 20 or so minutes. In the solar applications, you need to factor in things like the direction of the sun. You don't want to have the sun directly behind you when you're carrying out the survey, because that will cause a large reflection on the solar panels, which will skew and mask any potential anomalies. You need to ensure the camera is correctly set up. You need to make sure that things like the emissivity of the object you're looking at is programmed in to give you the accurate temperature readings. That can be changed in post, but you need to know the material of what you're looking at and any emissivity values of that so that you can get that accurate temperature afterwards. Now, focus, generally speaking, doesn't apply to drone cameras. However, we have seen the focus drift in some cameras. Normally, it's just a rotation of the lens with a special tool, but this needs to be set up at the start to make sure that your subject will be in focus, because that is something you can't change in post. And I have mentioned file format on here because I have known people to go out and do a survey of the solar park, and they haven't switched on they haven't switched to the radiometric file format, so they've just got pretty JPEG images. Of course, make sure the lens is clean. Any dirt, dust, fingerprints can skew the data, and you then also need to record your environmental data, because there are external influencing factors, such as what we call the reflected apparent temperature. On a clear sunny day, you're going to be getting the temperature itself is going to be affected by the sky, any other heat sources around it, and you'd record all of this sort of information on the ground, any cloud cover, that sort of thing. Data capture, I mean, once you've hit go, generally speaking, it's fairly straightforward and nearly always automated nowadays. But we have heard of certain flight planning applications being quite buggy and they're not necessarily triggering. So you need to ensure that you do a test flight to make sure everything's working fine and that the data is being collected correctly. It is, generally speaking, better to do smaller areas with thermal imaging cameras, because you are going to notice a temperature drift between the nukes where that shutter's coming down, and you could be midway through a flight and the shutter will come down and it will then sort of skew your temperature data. And if the weather changes drastically, it goes from being bright and sunny to very cloudy as well halfway through a flight, then that will affect the temperature readings as well, and so you need to factor that into it. This is, of course, not necessarily applicable in all instances. If you're just looking for relative temperature differences, so you don't care whether it's exactly 15 degrees, but you want to see anything with, say, a 5-degree difference, then it doesn't necessarily apply. Data verification. Now, this is, I'd say, something you'd normally do this just before you leave site, but after each flight, we'd recommend that you do it to make sure that the image data has been captured correctly. Sometimes you might find the camera triggers just as it's performing that non-uniform calibration, and that will potentially either give you just a blank image, which isn't ideal if it's covering a large part of the subject matter that you're after. Of course, you want to make sure that you capture it in the correct format and that you have the particular subject focused on and in those images. Now, post-processing is something that's going to differ from application to application. But this is generally where you would filter through your data and remove any of those bad images. Certainly in the built environment and the solar side of things, you would do what we call normalizing the data, where you would ensure that they all have the same thermal image, the temperature span. So, minimum -5 to +15, for instance. They all have the same palette, all have the same image parameters, that's emissivity, reflected apparent temperature, and so on and so forth. And you can normally do this in a program like FLIR Thermal Studio Pro, where they have quite a good batch image editor, and that will enable you to select all your parameters first and then hit convert, and it will edit all of those images and make sure they're nice and uniform, which is probably, I would say, necessary when you are producing, say, thermal index maps, where some of the software is reliant on what's in the color makeup of that image as reference points, or you're just stitching them together to create panoramas, or when you're wanting to be able to compare different parts of the same object. This is also when you would be able to then input your environmental data that you captured just before the flight. So a bit of a shameless plug here for Thermo Converter. It's a bit of software that we developed because we were having all sorts of issues with the native and proprietary thermal imaging analysis tool that DJI supply with their thermal imaging payloads. It's not very intuitive, it's very big, and it's missing a lot of features to enable you to, say, batch edit the images and to produce those reports. So we developed this piece of software that enables you to take the DJI format, and soon it will take the Autel format as well, and it will convert it to GeoTIFFs if you're wanting to then import it into something like Pix4D or Agisoft. And it will convert it also into the FLIR format of an RJPEG. So you can then use it in your existing workflow if you've already, if you're already using FLIR cameras. And we are also looking at being able to export to the Fluke file format as well. We are shortly going to be adding the batch edit capabilities to it, so that we can, so when you choose to export your data, you can make sure it's all normalized before you then export it, just to then remove that additional step. So yeah, this then enables you to then import those images into FLIR Thermo Studio reporting software, so you can produce your thermographic reports for your client. And whilst it's in beta at the moment, we should have our beta release, which you can see a bit of a preview of here, that will be coming out next month. If you want to know more about that, then by all means, please get in touch. So finally, the analysis and reporting side of things. This is where you then input your data into the program of your choice. In this instance, it's Scopito, which is an online reporting platform, which will produce nice PDF reports on annotated thermal images. And you can highlight things like hotspots, and you can tag colleagues into it or share it with the client. And this is at the stage where you would then go through the data and actually look at what's in them and where the anomalies are. What could the cause be? Generally speaking, though, it's always advisable that you're never making assumptions about what the cause is. You're making suggestions for the next steps or for further investigation to be carried out to identify the exact fault. You can then also fine-tune the images as well if you find a particular image of interest, and you need to adjust the settings of that image accordingly to potentially locate any potential causes. And just an example of the software, you've got FLIR Thermo Studio Pro, FLIR Tools, DJI Analysis Tool, but there are dozens out there. You can then often produce PDF reports, which is then what you'd hand over to your client. If you're producing a thermal imaging report, particularly in the built environment and the electromechanical inspection side of things, there are strict requirements that they should have. I'm not going to go into too much detail on this because this is something that would be covered during thermal imaging training. But you can see here is an example thermal report. This is actually a ground-based one, but it's just an example of the file which had the necessary requirements. So you've got your thermal image. You've got a temperature scale just the right hand side of it. Let's start on this. You've got your temperature scale there. You've got your corresponding digital image, so you can actually identify what you're looking at. You have your environmental data. You've got the spot temperature differences, deltas, that sort of thing here, and then the comments on that particular image. In this type of survey, they use traffic light system, so it's been deemed a priority 3, which requires attention fairly urgently. So next steps. If you're looking to jump into the world of thermal imaging, then please get in touch. We can help you spec out the particular camera you might need for your application, or even whether your particular application you have in mind can benefit from thermal imaging. We can also advise on the training guidance on what courses you should be doing depending on your application. And so I also recommend checking out YouTube as well. There's absolutely tons of good videos on there which cover everything from the more in-depth science behind thermal imaging to then more specific drone-based applications. And yeah, I would strongly recommend getting yourself on a course after this as well. So I think that pretty much brings us near to the end. I don't know if anyone has any questions at all. Well, I think I can only take that as a good thing.
We have one in the Q&A box, Tim.
The using what from Rob?
Yep.
Okay, yeah. Right, so yeah, okay. Well, I think that's probably something that I can talk to you directly about. Yeah, we can discuss that afterwards. Yeah, but essentially, if you're using thermal imaging to look at how well an irrigation system is functioning, and that it could be a very effective tool for that. Particularly as you're spraying the water, you'll be able to see the areas it's covering the spray, and of course identify the areas that are not getting as much water, and you can then potentially complement that with something like multispectral imaging, where you'll be able to look at that crop health. But that's a topic for another discussion. All right, I don't see any others. So I'll leave it on this slide here. So if you do have any questions that do come to mind, or you're looking to sort of progress along the thermal imaging path, you've got the details on the screen there. You can contact me directly, just at tim@ether.global. But yeah, by all means, hope this was enough for everyone. I have tried to keep it as simple as possible because there is a huge amount to it, and it's very difficult to sort of squeeze it all within an hour. I know we've just gone over the or approaching the hour mark. So yeah, yeah, hope you enjoyed it. I'll be pleased to get any feedback afterwards. But yeah, thanks for attending. We will also email you a copy of the webinar recording afterwards, and we'll make that accessible to anyone else should they want to view it as well. Okay, right, thanks everyone. Thanks for attending.